All right, welcome to The Explainer. Today, we are diving deep into, well, deep learning. The tech that's behind pretty much all the mind-blowing AI shaping our world right now.
So let's kick things off with a fundamental puzzle. Why is it so incredibly hard for a computer to just understand the real world? Well, it's because real-world data is just messy, it's chaotic. I mean, think about something as simple as recognizing a car. To a computer, a car at night, a car seen from the side, or a car half covered in snow, those are all totally different things. They're just different collections of pixels. These little differences, these factors of variation, make it almost impossible for a simple, old-school program to reliably connect a picture to the label car.
And that right there brings us to the absolute core challenge that held back AI for decades. It's called the representation problem. See, the success of any machine learning algorithm really comes down to the way you represent the data you feed it.
Okay, this slide is a perfect way to picture what we're talking about. Let's say you're trying to teach an AI to predict C-section risks. Now, if you give it a nice, clean doctor's report with structured features, simple things like uterine scar, yes or no, even a basic algorithm can start to spot patterns. Easy enough. But what if you give it the raw MRI scan? Just this massive grid of pixels. Now it's totally lost. I mean, what does one single gray pixel tell the computer about the patient's health? Absolutely nothing, right?
And that's the thing. The real world is exactly like that MRI scan. It's raw, it's unstructured, and it's just packed with all those messy factors of variation. So the challenge, the real trick, is to somehow pull out the important, high-level, abstract ideas from all that noise. But how on earth do you teach a machine to find an abstract concept, like the very idea of a car, when all it sees is a sea of pixels?
So that's the big question, right? How did researchers crack this nut? Well, they looked for inspiration from the best information processor we know of, the human brain.
And that led to this amazing idea of artificial neural networks, or ANNs for short. Back in the 1950s, early models like the perceptron were basically trying to create a super simplified version of how our brains work. They were these simple systems that could learn to sort inputs by adjusting a bunch of internal weights. Think of it like tuning thousands and thousands of tiny little dials over and over until you start getting the right answers more often than not.
But, and this is a big but, they were just a starting point. Our brains are on a completely different level of complexity. A single neuron in your brain can have something like 10,000 connections to its neighbors. The first ANNs, they were lucky to have a handful, mostly because the hardware just wasn't there yet. It really was like comparing a modern supercomputer to an old-school pocket calculator. So the real leap forward didn't come from making a better single neuron. Nope. It came from organizing them into layers, kind of like how our own brain's visual cortex is structured.
And this is where the magic really happens. Look at how this works. Each layer is basically building a more abstract, more complex idea than the layer before it. So the very first layer is just looking at raw pixels and learning to spot simple things like lines and edges. Then, the next layer takes those edges and learns to combine them into corners and basic shapes. The layers after that start piecing those shapes together into parts of an object, like a wheel or an eye or a nose. And finally, the very last layer puts all those pieces together to say, hey, that's a car, or that's a face. The network is literally teaching itself the best way to represent the world.
And that really gets to the core of why we call it deep learning. It's not just a buzzword. This whole layered structure is built on one really powerful belief, that the world is made up of concepts built on top of other, simpler concepts. A complex thing like a face is made of simpler things like eyes and a nose, and those are made of even simpler lines and curves. The more layers you have, the deeper your network is, the better it gets at learning this kind of natural hierarchy. Okay, and then this whole process got a massive turbo boost in the 2000s. Researchers found that if they replaced the older, kind of complicated artificial neurons with a much, much simpler one, it's called a rectified linear unit, or ReLU, everything worked better. It sounds totally backwards, right? A simpler part making a more powerful system? But that's exactly what happened. This simpler building block made it way easier and faster to train these incredibly deep and powerful networks.
Okay, so we've got layers, we've got these simple ReLU things, but how does the network actually learn which features to look for? How does it know which edges are important and which ones are just noise? Well, pretty simply, it learns from its mistakes. So, first things first, you need a way to measure how wrong it is. In the world of deep learning, we call this a loss function. And you can totally think of it like a score in a video game. Except here, you want the lowest score possible. A high score means your guess was way off. A low score means you're getting close. The entire goal of the training game is to get that score down as close to 0 as you can.
All right, so the network gets into this training loop. Here's how it goes. It takes an image, makes a guess, let's say, I think that's a cat. Then it compares its guess to the right answer and calculates that error score. And here's the clever part. It uses a bit of calculus to figure out exactly how to tweak each and every one of its millions of little internal dials, those weights, to make the error just a tiny, tiny bit smaller. This whole process of making these tiny nudges in the right direction is called gradient descent. And it does this again and again and again, millions or even billions of times.
Now, because these networks are so unbelievably complex, there isn't just one single perfect answer. It's not like solving a simple math problem. You can imagine the algorithm isn't just sliding down into one simple valley. Instead, it's navigating this insane high-dimensional landscape with countless hills and valleys and mountains. So the goal isn't to find the single lowest point on the entire planet. The goal is just to find a spot in a really, really deep valley, a solution that is so good it's incredibly useful in the real world.
So this amazing combination, these layered ideas and this process of learning from mistakes, it didn't just pop up out of nowhere. It actually unfolded over decades in what you can think of as 3 distinct waves.
The first wave, back in the 40s to the 60s, was cybernetics. That's when the core brain-inspired ideas were born. Then you had the second wave in the 80s and 90s, called connectionism. That's when they figured out the key math for actually training networks with multiple layers. But for decades, the ideas were just too big for the computers we had. They just couldn't scale up. And then came the third wave, starting around 2006. This is the one we just call deep learning. And this is when everything, and I mean everything, changed.
So you have to ask, what happened? What made this recent wave so explosive? Well, it was basically a perfect storm of 3 things coming together at once. First, the internet gave us an unbelievable amount of training data. Pictures, text, you name it. Second, the video game industry of all things had been developing these super powerful graphics cards, GPUs, that just so happened to be absolutely perfect for the kind of math these neural networks need to do. And third, when you combine that massive amount of data with that powerful new hardware, suddenly these models started achieving mind-blowing results, solving problems with an accuracy that people thought was decades away.
And this, right here, reveals both the incredible power and the deep mystery of deep learning. See, we haven't just programmed a computer to follow a set of rules. We've built a system that learns its own rules, that creates its own internal picture of how the world works. And that leaves us with a really profound question to think about. What happens when a machine's way of understanding the world becomes so complex, so alien, that we humans can't really follow its logic anymore? Now, that is a question we are all going to be dealing with for a long time to come.